Welcome to Physical Chemistry 1 Laboratory. I am Dr. Min Soo Lim, and I will show you how to carry out the lab in the experimental and theoretical aspects. You will do a 2-week-long experiment titled Freezing Point Depression of Strong and Weak Electrolytes. I want you to follow my instruction thoroughly, slide by slide. After you complete this online pre-lab lecture, you should take an online quiz that is posted on the 12. You may watch this video as many times as you need, but you have only one chance to take the quiz. You will determine the degree of dissociation of a weak electrolyte, which is monochloroacetic acid, by observing the change of equilibrium constant as the concentration of monochloroacetic acid changes. You will also determine the degree of deviation of a strong electrolyte, HCl, from the ideal behavior by observing the change of experimental and theoretical G1 values as the concentration of HCl changes. Electrolytes are substances that dissociate into ions in water, making electrically conducting solutions. The electrolytes that partially dissociate into ions in water and makes the solution weakly conductive are called weak electrolytes. Weak acids and weak bases are weak electrolytes. A double arrow is used to represent the partial dissociation of a weak electrolyte. The electrolytes that almost completely dissociate into ions in water and make the solution strongly conductive are called strong electrolytes. Strong acids, strong bases, and soluble ionic compounds are strong electrolytes. A single arrow is used to represent the dissociation of a strong electrolyte. Colligative properties are the physical properties of solutions that depend on the quantity of solute particles or concentration, but not their chemical nature or identity. Several examples of colligative properties are freezing point depression, boiling point elevation, vapor pressure lowering, and osmotic pressure. You will use the freezing point depression to determine the degree of dissociation of a weak electrolyte and the deviation of a strong electrolyte from its ideal behavior. What is the freezing point depression? Pure water freezes at 0 Celsius and 1 atm, but the salt water freezes at lower temperature. It is called freezing point depression. Take a look at this phase diagram of water. 3 phases of water, solid, liquid, and gas, exist in the diagram, depending on pressure and temperature. Lines are drawn to define the boundaries of the 3 phases. They are called phase boundary lines. 2 phases coexist right at each phase boundary line. At a given pressure P star, the solvent freezes at Tf and boils at Tb. When a non-volatile solute dissolves into the solvent, the vapor pressure of the solvent decreases due to the enhanced solute-solvent interactions. This defines a new phase boundary lines. At the same pressure, the boiling point of solution increases from Tb to Tb prime. This boiling point elevation is represented by delta Tb. However, the freezing point of solution decreases from Tf to Tf prime. The freezing point depression is represented by delta Tf, and the delta Tf is what you should measure in this experiment. Please be aware that you will use molality for concentration, not molarity. The reason behind is that molality is temperature independent, while molarity is temperature dependent. Molality is the moles of solute over the kilograms of solvent. Both moles and kilogram mass are independent of temperature, making molality temperature independent. On the contrary, molarity is the moles of solute over the liters of solution. The volume of matter depends on the change of temperature, making molarity temperature dependent. Hydrochloric acid and monochloroacetic acid will be used as a strong and a weak electrolytes. The formula of monochloroacetic acid will be represented by Ha. In this experiment, you should make 0.250 molal and 0.125 molal solutions of hydrochloric acid and monochloroacetic acid. I will show you how to prepare a 0.250 molal and the 0.125 molal solutions of hydrochloric acid as an example. You should follow the same procedure to prepare the same concentrations of monochloroacetic acid solutions. Take note that 0.250 molal HCl is very close to 0.250 molar HCl. So, make a 0.250 molar HCl solution and take it as a 0.250 molar HCl solution. This is how to prepare a 250 milliliter solution of 0.250 molar HCl. The number of moles of HCl to make the solution can be easily found out by multiplying the molarity of HCl by the volume of the HCl solution, that is 0.250 molar times 0.25000 liters, which equals 0.0625 moles. The volume of the concentrated HCl to be drawn from a bottle equals 0.0625 moles of HCl times 36.46 grams per 1 mole of HCl. This conversion factor is taken from the molar mass of HCl. The next conversion factor is taken from the assay of the concentrated HCl, which can be found in the label of the HCl bottle. It is 37.4%, implying that 100 grams of concentrated HCl solution in the bottle contains only 37.4 grams of pure HCl. It also implies that the remaining mass, 62.6 grams, is the mass of solvent water. The next conversion factor is taken from the density of the concentrated HCl, which is 1 milliliter HCl per 1.19 grams of HCl. So, the volume of HCl to be taken from the bottle is 5.12 milliliters. Now, transfer a 5.12 milliliters of concentrated HCl into a 250 milliliter volumetric flask. Do not take the HCl directly from the bottle. Carefully pour sufficient amount of HCl into a clean and dry beaker and transfer the required volume of HCl from the beaker to the volumetric flask. Fill the flask with distilled water up to the mark. Put the stopper on and mix by slowly inverting the solution a few times. This is the 250.0 milliliters of 0.250 molar HCl solution. The next step is to make a 150 milliliters of 0.125 molar HCl solution by diluting the 0.250 molar HCl solution. Transfer 75 milliliters of 0.250 molar HCl solution into a 150 milliliter volumetric flask. Fill the flask with distilled water up to the mark and mix by slowly inverting the solution a few times. Now, you have 150.0 milliliters of 0.125 molar HCl solution and the remaining 175.0 milliliters of 0.250 molar HCl solution. Place 2 solutions of hydrochloric acid, 2 solutions of monochloroacetic acid, and distilled water in an ice bath. Now, make an apparatus for measuring the freezing point of the 4 aqueous solutions. Place a 400 milliliter beaker into a 800 milliliter beaker. Fill the space between the 2 beakers with paper towel to make a good thermal insulation. Fill the inner 400 milliliter beaker about 1/3 full with crushed clean ice. Add about 100 milliliters of the chilled distilled water to the inner beaker. Assemble the apparatus as shown in the picture. Start the logo probe and let it draw a cooling curve. Stir the ice and water mixture well to achieve equilibrium. Temperature would maintain constant at equilibrium, drawing a plateau line. Pause the logo probe, open the cover, pour off water, and add an electrolyte solution. Put the cover back, continue the logo probe. Wait until it reaches another plateau line. The temperature at the first plateau region in the cooling curve corresponds to the freezing point of water, T0. The temperature at the second plateau region is the freezing point of solution, TF. The freezing point depression is represented by delta TF. You should report 4 delta TFs, 2 for the 2 HCl solutions, and another 2 for monochloroacetic acid solutions. After completing the freezing point measurements, you should transfer 3 10 milliliter aliquots from each solution to 3 Erlenmeyer flasks for titration to determine the concentration of the solution. So, you should prepare 200 milliliters of 0.100 molar NaOH standard solution. How much NaOH should you transfer to make the solution? Here is a simple math to determine the gram mass of NaOH that you should measure out. Since you will use 99.8% pure NaOH, let's put 0.998 first. Put X grams for the unknown mass of NaOH. The next conversion factor is from the molar mass of NaOH and converts gram mass of NaOH to the moles of NaOH. Divide the moles of NaOH by the liter volume of the solution, which is 200.0 milliliters or 0.2000 liters. This should be equal to 0.100 molar. The gram mass of NaOH should be 0.8016 grams. The little bar on the number 1 represents the last significant digit. Measure out 0.8016 grams of NaOH and transfer it to a 200 milliliter volumetric flask. Add distilled water to the 1/3 of the flask. Mix thoroughly, followed by adding additional water up to the 200.0 milliliter mark on the flask. Put the stopper on and mix by inverting the solution a few times. And this is a 200 milliliter solution of 0.100 molar NaOH. Here is a problem that you may have due to the hygroscopic property of NaOH. NaOH has a strong tendency of absorbing moisture from the air. Consequently, the concentration of NaOH solution would not be the same as you expect. So, you should standardize it with a primary standard, which is 0.100 molar KHP solution. Take note that KHP is not hygroscopic, and you can make a KHP solution with greater accuracy and concentration. prepare a 0.100 molar KHP solution with the same procedure to be used for the preparation of 0.100 molar NaOH solution. Now you are ready to determine the concentration of NaOH solution by titration at least 3 times with the KHP solution. You can use the standardized NaOH solution to titrate the 3 10 ml aliquots of each electrolyte solution. Open the cover of the calorimeter and immediately draw 3 10 ml aliquots with a 10 ml volumetric pipette and transfer each of the aliquots into a pre-weighed, clean and dry 50 ml Erlenmeyer flask. Warm each 10 ml solution to room temperature. Weigh and record the mass of each solution. Add 2 to 3 drops of phenolphthalein into each solution. Titrate each solution with a standardized 0.100 molar NaOH solution. Record the dispensed volume of NaOH solution and calculate the moles of acid that is present in each 10 ml aliquot. Now, I will show you how to determine the molar concentration of a 10 ml aliquot from each acid solution. Suppose that the concentration of standard NaOH solution is 0.100 molar. The dispensed volume of NaOH solution is 2.30 milliliters, and the mass of solution is 9.981 grams. Be aware that you should use the actual concentration of NaOH solution that was determined by the previous standardization step. However, in this demonstration, I assume the concentration of NaOH to be 0.100 molar. The number of moles of HCl can be easily calculated by multiplying the molarity of NaOH by the dispensed volume of the NaOH solution, that is 0.100 molar times 0.00230 liters, which is equal to 2.30 times 10 to the negative 4th moles. The mass of HCl is the moles of HCl times the molar mass of HCl, which is 2.30 times 10 to the negative 4th moles times 36.46 grams per mole, and it is 8.39 times 10 to the negative 3rd grams. The mass of solvent water is the mass of solution minus the mass of solute, or HCl, which is 9.981 times 10 to the negative 3rd kilograms, minus 0.00839 times 10 to the negative 3rd kilograms, and it is 9.973 times 10 to the negative 3rd kilograms. Finally, the molar concentration of HCl is the moles of solute divided by the kilogram mass of solvent. It is 2.30 times 10 to the negative 4th moles divided by 9.973 times 10 to the negative 3rd kilograms, which is equal to 0.0231 molar. If you complete the lab this far, then you would have delta TFs, an actual molar concentration of 2 monochloroacetic acid solutions, and 2 HCl solutions. In the next 2 slides, I will show you how to utilize them to determine the degree of dissociation of a weak electrolyte and the degree of the deviation of a strong electrolyte from ideal behavior. Since a weak electrolyte HA does not dissociate completely, we may construct an ICE chart that displays initial concentrations, change in concentrations, and equilibrium concentrations of reactants and products. If we put lowercase m as the initial concentration of HA, then the initial concentrations of H plus and A minus will be 0. Let's take alpha as fraction dissociated. Suppose alpha of a substance is 1. It implies that it dissociates completely into ions, meaning 100% of the substance dissociates. So, it is a strong electrolyte. If alpha of a substance is 0, then it does not dissociate into ions at all, implying that it is a non-electrolyte. So, alpha of a weak electrolyte should be in between 0 and 1. Suppose the HA is lost by alpha M. As a result of it, H plus and A minus are gained by alpha M. Consequently, the equilibrium concentrations of HA, H plus, and A minus are M times 1 minus alpha, alpha M, and alpha M respectively. Freezing point depression is a colligative property. Consequently, it depends on the concentration of solute species and does not depend on the chemical nature of the solutes. The total effective molality of all solute species is represented by M', and it influences the freezing point depression. Then M' equals M times 1 minus alpha plus alpha M plus alpha M, or simply M times 1 plus alpha. Please take note that M is the actual molality of HA that should be determined by titration. The equation above can be written with respect to alpha. That is, alpha equals M' over M minus 1. Equilibrium constant KEQ can be expressed with the equilibrium concentrations of HA, H plus, and A minus. That is, KEQ equals M times alpha squared over 1 minus alpha. M' can be calculated with experimentally determined delta TF using this equation. M' equals delta TF over uppercase KF times 1 plus lowercase kf times delta TF. Please take note that the freezing point depression delta TF is TF minus TF prime. TF is the freezing point of solvent and TF prime is the freezing point of solution. Uppercase KF is the molar freezing point depression constant and lowercase kf is the correction constant. The values of the constants can be found in the lab textbook. Now, you can determine two M', one for the lower concentration and one for the higher concentration. You can also determine two alpha values, one for the lower concentration and one for the higher concentration. Finally, you can determine two equilibrium constants for the weak electrolyte solutions, one for the lower concentration and one for the higher concentration. Strong electrolyte like HCl dissociates completely in ideal condition. In reality, however, as the concentration of solute increases, the interionic interactions between solute ions increases, and the chances of recombining anions and cations increases as well. Consequently, it causes the deviation of a strong electrolyte from the ideal behavior. The osmotic coefficient G1 in Debye-Huckel theory allows us to see the deviation of a strong electrolyte from the ideal behavior. Theoretically, G1 equals 1 plus log gamma naught over log x naught. Gamma naught is the activity coefficient of solvent and x naught is the mole fraction of solvent. Since gamma naught of the solvent in an ideal solution is 1, G1 for an ideal solution is 1 as well. In reality, however, the G1 deviates from its ideal value. The G1 values can be determined experimentally with this equation. Experimental G1 value equals delta TF divided by uppercase KF times nu times M. Nu is the number of ions dissociated from one molecule. That is, the nu for HCl is 2. M is the actual molality of HCl that is determined by titration. Now, you should be able to determine the experimental G1 values for HCl solutions of low and high concentrations. The theoretical G1 values adopted from the Debye-Huckel theory can be determined using sigma value. The sigma values for HCl solutions of low and high concentrations can be determined graphically. Take note that sigma is a function of kappa A, and kappa A is approximately square root of actual molality of a HCl solution. Sigma values with respect to kappa A values are tabulated in the lab textbook. I want you to plot the sigma values with respect to the kappa A values using a spreadsheet software like Microsoft Excel. Find the equation for the best fit line of the plotted data points. Calculate the kappa A value of a HCl solution using the equation above, which is kappa A equals square root of actual molality of a HCl solution. Plug the kappa A value into the equation of the best fit line to determine the sigma value of the HCl solution. Then, the theoretical G1 value can be determined with this equation. Theoretical G1 equals 1 minus 0.38 times sigma times square root of M. Now, you should be able to determine two theoretical G1 values, one for the solution of low concentration and one for the solution of high concentration. I want you to include at least the following items in your lab report. Number 1. Include 4 cooling curves in your lab report. 2 for HA solutions of low and high concentrations, and another 2 for HCl solutions of low and high concentrations. Number 2. Report an equilibrium constant for HA solution of low concentration and another equilibrium constant for HA solution of high concentration. Does equilibrium constant change as the concentration of HA changes? If so, what would have caused the change? Number 3. Report the experimental and theoretical G1 values for HCl solutions of both low and high concentrations. State whether both experimental and theoretical G1 values exhibit the same trend as concentration changes. Discuss what would have caused the deviation of G1 from the ideal value as concentration of HCl changes. Explain it in the perspective of the change of the degree of interionic interactions as concentration changes.